This C++ code demonstrates the use of function pointers but also reveals a subtle and dangerous mistake. First, let's clarify what a function pointer actually is. A function pointer is a variable that can store the address of a function, allowing you to call the function indirectly through the pointer. It's especially useful when you want to pass functions as arguments, store them in data structures, or decide which function to call at runtime. Crucially, a function pointer must match the exact signature of the function it points to, including parameter types and return type. Otherwise, you risk undefined behavior. In this example, we first declare a function pointer designed to point to any function that takes an int as a parameter and returns void. It's assigned to a function with a matching signature, and when the function pointer is called, it works perfectly. The correct value is passed, and the function executes as expected. When we run the code, we can see that. The problem arises when the same function pointer is later reassigned to a different function that takes a double instead of an int. To make this compile, a reinterpret cast is used to forcibly convert the incompatible function type. This tricks the compiler into believing the new function has the same signature as the pointer. However, at runtime, the function still expects a double, and the function pointer is providing an integer. Because calling conventions and argument passing depend on the function's actual signature, this mismatch can lead to corrupted data being passed, stack corruption, or even crashes. On some systems, you might get lucky and see the correct value printed, but the behavior is not guaranteed and should never be relied on. The fix is to respect type safety and ensure the function pointer signature exactly matches the function it points to. If you need to point to multiple functions with different signatures, you should use separate function pointers for each signature or redesign your code using templates or polymorphism to avoid the need for mismatched casts entirely. This example highlights both the power and danger of function pointers in C++. They allow dynamic function calls and flexible program structures, but type safety must be respected at all times to avoid undefined behavior.